So I have seen quite a few of you before at the time when I was full-time AWR. So as Olivia was mentioning in the morning, I have a kind of dual role. So I work essentially 3 days a week at Optenni Limited and 2 days a week still with AWR. And so my role in AWR is still basically supporting the electromagnetic related customer problems. So it's just having a little bit more focus on that. So this is how it influences my AWR role. Optenni Lab is a tool which is created for antenna analysis and matching circuit synthesis. And I'm trying to highlight certain special features of Optenni Lab, how it can be used to tackle some of pretty tricky problems that there are in the antenna matching. If we think about, say, simple antenna matching problem, that could be a narrowband, and if we can assume if we have lots of space, then we can use perhaps ideal or nearly ideal elements like transmission lines or stuff. Narrowband matching is not the problem. But when, as we saw with the Infineon presentation, the modern communication systems, they actually are very, very complicated. And from the antenna perspective alone, it's a very big problem. There are many radio systems. There are many physical antennas in a very small physical space. And this is what is causing lots of troubles for the antenna engineers. And in my presentation, I will be talking and showing some demonstrations on especially multi-antenna matching problem. So I have created just recently, this week I got the samples of, this is a dual or two PIFAs in one and the same board, tuned in different frequency bands. And so we can analyze this. So far I still have only the simulation results. So I've used AWR AXIEM to simulate these boards. I have a couple of other examples here as well. One quite interesting one is a waveguide-backed slot antenna. And this one, according to the theory, should have a property of a very good isolation between the elements. And so I just last night actually was running the simulation, and we can look how the result looks like. Okay. So to summarize a little bit what Optenni can offer for simultaneous matching of several antennas. The special design concern is that it involves first of all optimization of efficiency rather than the reflection. So it's quite easy to measure reflection or impedance, but it's different from the efficiency. If we keep adding, say, discrete lossy elements, then we may end up a situation where we have a really nice return loss, but it's very lossy, and that's no good. So from the beginning, it's very deep in the Optenni philosophies that we focus on the efficiencies. And also the antenna-to-antenna isolation is a concern. And so it's the user choice that, depending upon the geometry and how the antenna performs, the user can set constraints also related to the isolation. And so it's a coupled problem. So when you make, say, if we have a two antenna system, then if we increase the efficiency of one antenna, then it tends to make the isolation worse. So you are pulling more energy, but part of the energy is actually coupled to the other victim element, and vice versa. And so we have to kind of keep, say, several design targets met at the one and the same time. There are certain kind of sub-tools that you can make very quick analysis of so-called electromagnetic isolation. It's just I will show you in a minute. It takes just say a second or so, which characterizes the situation where, say, all the antennas are perfectly matched at every frequency. And then we are measuring the kind of worst case isolation. And so this is a way to characterize and kind of sort different antenna candidates. So if we have a kind of inherently good electromagnetic isolation, then it means that we can make as good matching as we want, and there is no possibility that the isolation would get bad. And that will be very neatly seen actually with this waveguide backed thing, so we can have a look a bit later. And so this is kind of a pre-selection tool. So we will move forward and say consider a couple of test cases. And so to start with, indeed what I showed initially, 2 PIFA antennas on the board. And so intentionally, so the idea is that the size might be roughly, say, of a smartphone or so, and they are placed relatively close to each other. There is one of the antennas which is designed for, in this case, rather arbitrarily, but I just selected WCDMA bands 1 to 3, so 1710 to 2170 megahertz, while the second antenna is for the wireless LAN, 2.4 gigahertz. And so the motivation, say, for the isolation concern is that there is the WCDMA transmitter has a high power, and it's close to the victim antenna in this case. So we have to kind of worry about the possibility that the antennas get coupled. And so this is how the geometry looks like. And so maybe I go to the demonstration. It's easier to discuss that way. So I launched the Optenni Lab tool. And basically, Optenni Lab operates with, or the user input is the S-parameter file, a description. In multi-antenna system, it has many ports. There can be also many ports for the reason that we have a layout included in our model, and we have ports for the kind of placeholders for the discrete elements. It can also connect directly to network analyzers, such that you can bring Optenni Lab into lab and, for example, trim your antenna while it's connected to the impedance measurement on a VNA. So Keysight and Rode VNAs are supported at the moment. We are working with Anritsu and probably some others downstream. But this is, we consider this is an important mode because, say, modeling antenna is one thing and having the prototype is another thing. And so because the lab work, it involves trimming and stuff, and so it's practical that the tool is also close. So in this case, I have this 2 antenna simulation result. Right. So the original, this is kind of now representing the plane measurement without any matching elements. And the light blue curve here is the S21, which is the coupling from one antenna into another. And when I mentioned the electromagnetic isolation, here we can choose analyze electromagnetic isolation, and then we might have many antennas, and then we can consider kind of one antenna pair at a time. So I can nominate that my first antenna is A and antenna number 2 is B, and OK. And so it's like a fraction of a second. So what happened behind the scenes, at every frequency there is a perfect conjugate match with ideal lossless elements. And so this tells us that, say, our target frequency range is somewhere 1700 to 2100. So there is a potential coupling of the level of the range of minus 6.5 dB, which is quite much energy coupled potentially. So this is something that we can take into account when we decide upon the matching circuit. So with multi-antennas, there is a multi-port option in the tool where we choose then, first let's set the frequencies for each of the ports. We can add also stop bands, so we can sometimes, or quite often, the antennas must not radiate at certain frequencies. But here I can choose, there are kind of pre-canned bands for the communication system, so I just cover all the 3 bands for that one single antenna. And there is a target level for efficiency in decibels, so minus 1 dB is the kind of the nominal target. You can set it differently. That's for port 1. For port 2 we use the 2.4 GHz wireless LAN. For the isolation, we can add isolation target also for both bands. So let me take again this WCDMA I-III at 1710, and I set my target level minus 15 decibels. And then I add a band for the wireless, again minus 15, and OK. Then we need to choose what kind of topology we want to consider. So we can, here is kind of a sketch of the situation. We have a system, this is essentially my board with its 2 antennas, and then we have a kind of placeholder for the 2 matching circuits. The defaults are 2 components. The topology is created automatically. So the tool scans through a number of topology candidates. And so this is not only matching criterion optimization, it's also optimization over the choice of the topology. It's not necessarily clear in advance which works and which won't. So let's go with the defaults. And then I just click OK. Optenni Lab is optimizing, it's using all the cores if you happen to have a multi-core machine. And this is now really the case is that we have a relatively demanding situation where we are trying to manage matching of 2 antennas, but also the isolation between them. And here we get the screen resolution is a little bit poor, so let's look at one thing at a time. So Optenni Lab found a candidate, and here is the report, say regarding the efficiency on each band. So we reach minus 1.6 dB, which is okay. And for the isolation, so we were warned by the electromagnetic isolation measurement that we can, in bad case, we can reach minus 7 dB coupling. But this matching circuitry is now such that it guarantees close to minus 15 dB isolation between the elements. This is how the circuit then looks like. So this is now with ideal elements. But indeed, so like for port 1, there is first a shunt element and then the series, while it's vice versa for the other port. And figuring this out with the general purpose optimizer would be quite time consuming. And in fact here, so let me put them aside. Here we have, if we want to scroll the other topology variants, then they are arranged here on the project tree. So maybe I call this 2 ideal elements. And so here we have the different variants of the topologies where we can recognize certain interesting things, that sometimes it happens that you get almost as good performance, but like it seems like one of the almost good topologies is one in which we have very small inductance. This tells that actually even with one single element we get a quite okay result. And so it's worthwhile to scan few top topologies, kind of building understanding on what is the expected performance. Moving forward, we can relatively straightforwardly say push our luck a little bit. Maybe the target of 15 dB is something that we can't compromise, and then we add number of elements. So let's try with 3-element matching for both ports. Again, it's a user choice. It might be that one of the antennas is such that it needs more help from the matching circuit, while the other one might not. But let's consider a symmetric case and have a 3+3 element matching circuit synthesis. The number of potential topologies is huge now. There are 6 elements, each of them can be L or C, each of them can be shunt or series. So there are 4096 topologies. Here we have, say now 3-element matching circuit which reaches this -1 dB constraint or this target for the efficiency. And in fact, the isolation is guaranteed for both bands below 15 decibels. Okay, so we might think that, okay, this is perhaps good, and so let's try with some library elements. So we are about 2 GHz range, and we can implement it using library components. And what actually happened, so I moved the circuits, by the way, they can transfer to CST Design Studio if you have a license, to Microwave Office or to FICO. There is no extra licensing involved with these links. So as soon as you have these tools, this link works. And so you can transfer the circuit to Microwave Office here, and the circuit is then brought into Microwave Office. Okay, so I did it before, and then I used the Microwave Office libraries and picked the values that kind of the immediate idea that, okay, you had about 15 picofarads capacitance. Let's look the library, choose 15 picofarads. What happens doing so? So here again, sorry for the small screen, I try to maximize. I'm making a comparison between the ideal versus library elements. The ideal response are the solid lines. And here, especially the green line here, we had the nice impedance, or the impedance matching the notch. The light blue is the efficiency, it's really nice. But when we consider the library elements, then the first antenna is almost okay, but the second antenna resonance moved here, and the efficiency drops to -14 decibels. So there is nothing put through in practice. So it's a point getting back and trying to understand and analyze. So the thing that happens is that this indeed provides, theoretically speaking, a nice matching, but there is a very small inductance between very large capacitors. So this is not a nice topology. And you can tackle this in advance by running a simple tolerance analysis, running 100 iterations, and then you can see that it's a little bit dim, sorry for that, but we can see that the kind of the variation around this second antenna operation range is blurred. And here we can see that, say, in terms of the efficiency, there is kind of a big drop, like 3.5 decibels drop. So there are certain kind of default tolerances that I'm applying for my inductors and capacitors. And this means that it's not really a stable topology. So while if we scan through the other topologies, here we have other one, the next one in the list. Its performance is almost as good. It reaches -1 dB efficiency, and it keeps this -15 decibel isolation. And the topology, say, by naked eye, this looks more healthy. So the values are okay. So we can let Optenni Lab make decisions for the real elements too, and optimize over the libraries. So if I go one more time to the multi-antenna matching, I can choose also my components from library. So just this week I bought a designer's kit from Coilcraft 0603 CS, high Q inductors, and Murata's GQM18. This size because it's easier for me to solder 0603 than any smaller ones. That's the only reason. And because I intend to move forward with these. Okay. And so Optenni Lab is now optimizing over the libraries. And so again, the same thing, there are topology optimization and selecting good values from the libraries. So it's very easy for me. I have my Murata kit and my Coilcraft kit. 1.2 picofarads here, 2.2 here, 1.1 here, and so the other elements. And how about the performance or the expected performance? We get -2 dB for the isolation, and still this -15 dB guaranteed for the, -1.2 for efficiency and -15 guaranteed for the isolation. And so let me try to bring forward how it looks like. So here is the matching, kind of as such. That's not that terribly important. The more important is the efficiency. And I have to point out that measuring for multi-antenna systems, measuring the efficiency, it can be quite tricky with the circuit simulator. So the way how to do it in AWR, for instance, is that you have to, use the power meter. You could otherwise use this network terminated port, but you have a multi-port system, and say what the ports are not terminated by 50 ohms. They are terminated by the matching circuits. And so therefore, say, unfortunately, it's a little bit clumsy way. It can be analyzed in microwave office using the power meter, but you need a nonlinear port and a nonlinear license. So that's a kind of a side effect a little bit. But it could be kind of, with this link, you can then take the design from Optenni Lab one click, and then you can consider, for example, if there are small inductances, you can consider implementations, say various techniques that you might have microwave office models already. Roland was asking about the possibility to use transmission lines. I just quickly show that one. Say, suppose I'm happy with the topology. Otherwise, I can kind of use this topology as a template. And for example, for the second port here, I can, okay, so arbitrarily, or let's take one of the shunt ones. Suppose I want to replace this shunt capacitor by a transmission line. So I can delete this guy and add, say, a microstrip, either microstrip line or generic transmission line that is characterized by its characteristic impedance, which can be also optimizable. Sometimes small shunt capacitances, they might be kind of essentially a wide microstrip line, relatively short. Or there are also microstrips that you can optimize its length and width for instance, and set limits for the optimization. Okay, I didn't specify the substrate, so I'm just for the demonstration's sake, I select the orientation. I can choose whether it's open circuit or grounded stub. Say, suppose it's an open circuited transmission line. Okay, no, okay, I need to select its place properly. But this way, you can, let me see, delete coilcraft, insert before coilcraft, add a transmission line in parallel sense open circuit. And here we have a kind of a variant of this topology. And when I click OK, OK, I didn't try if this works, so fingers crossed. But now it's optimizing using otherwise library elements, but for that one shunt, it's using transmission line. So this is, it's basically it's a user choice. But indeed, what I mentioned earlier, we are also working on the idea whether at least up to certain point, if it makes sense to offer possibility for kind of automatic topology consideration as well. It's like tricky. Sometimes the transmission lines are naturally shorted, like if it's a waveguide section. Or if it's a microstrip, then the grounding involves also some inductance and so on. But nonetheless, we found a way. Again, the response is good. 17.9 millimeter of ideal transmission line. Open circuited, and then here we go. There is the question of, say, layout parasitics. So depending upon the frequency range a little bit, but the matching circuit area, it spans a certain dimension. It has its electrical length too. And it is possible to use the same or similar mechanism to take that also into account. But you need to have typically an EM simulated model for the layout. And so you need to define so-called series ports as the placeholders for your discrete elements. And then it is possible, you know the topology already from the first shot. And then you can use this multi-antenna matching in a mode in which there are kind of two ports are acting as antennas, and the rest are representing the matching elements, and then the tool optimizes over the libraries. And so, like in this case, it turns out it's typically kind of a fine-tuning thing. So the optimal suggestion will change kind of to the neighbor elements. Like for antenna 1, it was first 1.3 picofarads, but because of the layout details, the suggestion will be 1.1, and similar kind of small fine-tunings for the other elements.
What did you, sorry?
Yes.
You put into you put into the position of the screen?
Yeah. So what I have is, in this case, 2 ports. It's an electromagnetic simulation result. 2 ports for the antenna inputs, and 3 plus 3 ports for the matching ports. 8 port S-parameter file. So let me open a new project. Read impedance file. It has altogether, okay, I named it 2 antennas with ports for matching elements. So this is this as such does not mean anything yet, but when I know that this port 1 and port 2, they are nominated for they are the input ports. Sorry, I wanted to. So I just this a little bit clumsy way we are again working with the kind of making this visually better. For each of these, the ports 3 till 8, I'm essentially shorting to the local negative terminal. So now in the background I had the idea that these are series ports, such that the negative terminal is kind of the other member of in the, say, I'm placing a capacitor, say, between the line and the local ground. So the negative terminal here is always referring to the other member in the series port group. And so I can then choose my topology, like port number 3, in my terms, it corresponds, if I remember well, is the first shunt element, which is then a capacitor. So I choose here that I select a capacitor from a library, and I'm choosing my Murata library, and I let it optimizable. And now I have kind of placed in my kind of layout representation my element there, which is then optimizable. So Optenni Lab is finding the good value. So you can kind of, if you are worried about whether or not the layout plays a role, you can kind of separate, take the measurement for the kind of the radiator, and then have a kind of a circuit model or an EM model of the layout portion. Typically what we see is a fine-tuning effect. And so if it's a dramatical change, then there is probably something else to be worried also. And say, to be entirely honest, the models, the library models, the Murata, Taiyo, Yuden, etc. models, they have their kind of limits as well. So it might be, we are working on say, studying when we say get the prototypes moving forward, which effect kind of masks the other. It may be that the layout influence is smaller than the model accuracy anyway, or it may turn otherwise. So that's still an open question. But what I'm saying, it's possible to, if you have a good model or verified model yourself, you can also create your, say, own libraries in so-called MDiff format. So MDiff is an okay format for Optenni Lab. And if you know that your EM simulator is giving you good results for the layout, then you can kind of save one extra iteration. Yeah. And okay. Sorry. And so if we didn't do this fine-tuning, then typically we will see, say, some frequency shifts. So that's how layout influences, or say the layout details. It's quite typically, and so the Optenni Lab can, in advance, kind of counterbalance. That's kind of in a nutshell. Right. I think I'm soon running out of time, so I wanted to show you especially this slot antenna case, as it's the most fresh one in the sense that the simulation results came last night. So I read the impedance file. This is a waveguide pair. And so this is how the initial results look like. By the way, if you have several of those sub-projects, they can all be open in one and the same session. So this is, you can have many of them open at one at the same time. So what we have, they are similar, they're intentionally the same antennas, they're operating at exactly the same range, so it could be like, it could be part of antenna array or something like that. And we can see that especially this S21, the isolation at the inherent matching is about minus 12 dB, but there is a kind of a promising notch here at about 2.8 gigahertz. Let me scale the axis differently. And so if I perform again this electromagnetic isolation, which is the worst case thing between now these two antennas, then we see a really nice deep notch. sorry, here at 2.8 gigahertz. So the isolation, whatever you do with the matching circuits, will be better than 30 dB, at least according to the simulations. So which means that if we want to, depending upon what we want to do with this antenna, if we want to do an array, for instance, then 2.8 gigahertz is a good frequency for this one. Then you can design, say, the feeding without consideration of the coupling. There's another interesting measurement, bandwidth potential. Bandwidth potential means that if we assume a conjugate match two element, what is the bandwidth at each frequency? And so we can see that, again, in a matter of a fraction of a second, we see that this antenna is such that at about 2.7 gigahertz, we can achieve, say, well beyond 500 megahertz band at my specification was minus 6 dB, was the return loss level. So this is a well isolating in one frequency and slightly different frequency. You can achieve very wideband behavior. If we add marker, say 2.7 gigahertz, sorry. Here, okay, marker frequency. Scaling, 2 to 3. So 2.65 gigahertz, we can get the very wideband antenna. But if we look the electromagnetic isolation at this frequency, then it's potentially reduced to minus 12 dB. So the notch is really deep. So we can't make well isolated very wideband, not necessarily. But we can make definitely a narrow band, very well isolated antenna at 2.8 gigahertz. So it's again our choice. So I can define the band, say, let me call my own band, say, let's take 2780 till 2820, for instance. And I copy the other ports, the same frequency band, and I leave the isolation. I know it will be well isolated. So I leave it open. Automatic two components. And here we have a candidate. And what we can achieve the essentially ideal so it was already quite well matched, and this simple matching circuit with so narrow band provides ideal elements. It provides perfect efficiency, close to 100% if we have ideal such. And if we look the S21, so let me try to arrange these again a bit differently. Axis scaling, let's take minus 40 dB. And here we have the S21 is actually, it's below minus 25 dB. And in the middle of the band there is this excellent isolation. So we have created a, say, 40 megahertz band with better than 25 dB isolation. Or the other approach could be that, okay, perhaps we want to have a wideband and we are not so much worried about the isolation. It depends upon the application. One final thing, very quickly show you one other example. I'm running out of time, unfortunately, where let's take an antenna, which is here, its radiation resistance is very low. And so necessarily it will be narrow band also. So it's the S11 reaches minus 0.5. But nonetheless, we can design a matching circuit for this one. And the intended application here is actually to use it at 433 megahertz. But the frequency is actually set using a tuning trimmer in the end of the antenna element. So in fact, okay, so maybe to make a long story short, I open a project that I said before. The idea is, again, I have simulated also the layout details, including now the trimmer capacitor port. This is now important. And I can optimize in a mode where I select kind of the other elements except the trimmer using library elements. It turns out that this circuitry is so much sensitive to the capacitance value that the stepping that we have in a library element is impractical, which means that it can't be within any reasonable tolerance to be kind of centered at 433 megahertz, except using a trimmer with the continuous range. And so I have made a combination of such, say, libraries and then this trimmer element. I have also included an assumed equivalent series resistance loss in my trimmer element of in this case 0.3 ohms. But so the synthesis now involves kind of 3 library elements and the continuous trimmer value. And so I can reach my goal at 344 megahertz by trimming it close to 1 picofarad. But because there is always manufacturing tolerances that they kind of would otherwise mask the problem, and I can't use library elements to get so narrow band matching here. So that's just one example. Indeed, I think I have to stop here. It seems like I could continue also talking about the tuners. Like in the Infineon presentation, I paid attention to one of the first slides of the architecture, where the antenna in practice, it might have a switch and then a bank of different capacitors here, and then we control the switch position. We can change the band. This mode is supported as well. And so, of course, offline we have then possibility to discuss, say, during the breaks more, and you in your seminar bag you have my contact details also. I'm more than glad to, say, continue discussing afterwards. Okay, so thank you for your attention.